mathematicians. Today we see one nice problem from linear algebra. Let lambda and me be two distinct eigenvalues of a 2 by 2 matrix. Then which of the following statements must be true? So the options are a square has two distinct eigenvalues. A cube equal to lambda cube minus mu cube by lambda minus mu times a minus lambda mu into lambda plus mu times I. Then trace of a power n equal to lambda power n plus mu power n for every n. Fourth option is a power n is not a scalar multiple of identity for any n. Okay. So some options are immediately you can notice that it is wrong. So that is why I already marked the answers. First option is a square has distinct eigenvalues. So it's given that a has distinct eigenvalues. Then a square has distinct eigenvalues they are saying, but what are the eigenvalues of a square? So if a has eigenvalue lambda and mu, then lambda square and mu square are the eigenvalues of the matrix a square. So basically the question is, if lambda and mu are distinct, does it means that lambda square and mu square are distinct? Like you can easily come up with some example, like for example 1 and minus 1 if you consider, then that squares are equal. Okay, so if you consider this matrix a equal to 1 0 0 minus 1, then its eigenvalues are 1 and minus 1, then its a square will be identity. Okay, and whose eigenvalues are 1 1. Okay, therefore a square has distinct eigenvalues, wrong. Yeah, and similarly, if you look at the last option, they are saying that a power n is not a scalar multiple of identity for any n, but for this particular matrix a square we are getting I. Okay, therefore this option is also wrong. Okay, so now if lambda and mu are the eigenvalues of a, then for a power n the eigenvalues are lambda power n and mu power n. Okay, therefore trace of a power n is equal to sum of the eigenvalues of a power n, that is lambda n plus mu n. Okay, therefore third option is correct. We only has to prove that the second one, that is a slightly tricky one, but whenever you want to write a square, a cube, a power 4, higher powers in terms of lower powers, you remember that you have to use Hamilton theorem. Okay, so basically you have to use its characteristic polynomial. So it's given the lambda and mu are distinct eigenvalues. When I solved the problem, I took it to be alpha and beta. Okay, so alpha and beta are the distinct roots of the matrix A. Then what is the characteristic polynomial of A? A is a 2 by 2 matrix, therefore the degree of the characteristic polynomial has to be 2. So if alpha and beta are two distinct values of A, then the characteristic polynomial will be x square minus sum of the roots times x plus product of the roots. Okay, so by Hamilton theorem, A satisfies its characteristic polynomial. Therefore, you get a square minus alpha plus beta times a plus alpha beta times identity matrix equal to 0. From this, you calculate a square. A square equal to alpha plus beta times a minus alpha beta I. Okay. So you got a expression for a square. Now you can find it for a cube, a power 4, any higher powers by multiplying suitable powers here. So I want a cube, so I multiply a in left hand side as well as right hand side. So left hand side I'll get a cube, right hand side a become a square, I becomes a. Okay, therefore now there is a square here, but we want a expression for a cube involving only a and I. Therefore, again for this a square also I substitute this previous equality, a square equal to alpha plus beta times a minus alpha beta times I. So we get alpha a cube is equal to alpha beta times alpha beta plus a minus alpha beta I minus this term. Okay, now this alpha beta can be, you can multiply inside, you get alpha plus beta the whole square times a minus alpha plus beta into alpha beta I minus alpha beta a. Now there are two a terms, so you group together, you get alpha plus beta the whole square minus alpha beta times a minus alpha plus beta times alpha beta I. Okay. Now if you use so this is a alpha square plus beta square plus 2 alpha beta. There is a minus alpha beta, so you get alpha square plus beta square plus alpha beta times a minus alpha beta into alpha plus beta into alpha beta I. Okay. So now we have come arrived at this expression for alpha a cube in terms of a and I. But here you have lambda cube minus mu cube by lambda minus mu. So in terms of alpha and beta, alpha cube minus beta cube by alpha minus beta. But here you have alpha square plus beta square plus alpha beta. So if we prove that these two expressions are same, so which two expression we want to prove to be same? This is, we want to prove that this is equal to alpha cube minus beta cube by alpha minus beta. Okay. Uh, Okay. So to prove that these two things are equal, what we will do that we will prove that this term into alpha minus beta is equal to alpha cube minus beta cube. Enough to prove that. So I am multiplying alpha minus beta into this term here. So alpha minus beta into alpha square plus beta square alpha beta. If you simplify, you will get alpha cube minus beta cube. Therefore, alpha square plus beta square plus alpha beta equal to alpha cube minus beta cube by alpha minus beta. Okay. Therefore, second option is wrong. Okay. Okay, guys. If you learned something new in this video, please click the like button and share with your friends and subscribe to my channel. Thank you.